We're going to take a look at relative rates of growth. All right, so the function y equals e to the x grows really fast. We're going to illustrate just exactly how fast that is. If we graph this, it would look something like this. There's our curve y equals e to the x. You can see that if our scales are both drawn the same, this thing starts taking off pretty much immediately. So if x is 3 inches, then y would be about 20 inches. If we went over to x is 10, you can see that the graph isn't even visible at this point because it's going up so steep. The y value there would be about 1/3 of a mile. And if we went out to just 44 inches, so not a couple feet, not too far, our y value is 2 million light years. So you can see that just a small move over in the x direction gives you an incredibly large change in the y direction. And if we go just 64 inches, the y value takes us to the edge of the known universe, 13 billion light years away. All right, the function y equals natural log of x, that grows very slowly. If we graphed it, it's the inverse of e to the x, so we would have essentially these same comparisons. So before we made it 12 inches or 1 foot up the y-axis, we would have to go 2.6 miles out to the right in the x direction. So y equals natural log of x does continue increasing forever. It has no asymptote. It just takes a really, really long time to make much progress going up, but it does approach infinity. The limit as x goes to infinity of natural log of x is infinity. Okay, so we're going to define what we mean by growing faster or slower or at the same rate. If f and g are positive for large values of x, then f grows faster than g, or equivalently saying g grows slower than f as x approaches infinity if the limit as x goes to infinity of f over g equals infinity, or if the limit as x goes to infinity of g over f equals 0. So just take a moment to think about this. If the limit as x goes to infinity of f over g is infinity, that means f is being much more dominant than g because it's able to take over and take the whole thing to infinity. So f is growing faster, g is growing slower. If we look at the limit as x goes to infinity of g over f, that approaches 0. That means the function on bottom must be dominating in order to bring this whole thing down to 0. So f grows faster, g grows slower. F and g grow at the same rate as x goes to infinity if the limit as x goes to infinity of f over g, or you could take the limit as x goes to infinity of g over f, equals some number L not equal to 0. So if that gives us any constant value, not 0, not infinity, we would say that these two functions grow at the same rate. Okay, a quick warning here to make sure we clear any misconceptions. According to this definition, y equals 2 times x does not grow any faster than y equals e to the x. So take a look at both of these. Now you might think, y equals 2 times x has a steeper slope, but that's not what we mean when we talk about growing faster or growing slower. So if we took the limit of one over the other, we get 2, that's a constant. By our definition, these grow at the same rate. So growing faster or growing slower does not have anything to do with the slope. It has to do with the magnitude of the two functions. Is there one that ends up completely taking over when we take the limit? And in this case, no. The limit as x goes to infinity is 2, so neither one of those is growing at a fast enough rate to pull this limit to infinity or down to 0. All right, we want to figure out which grows faster, e to the x or x squared. You might have an idea right off the top of your head, but let's find out using our definition. We take the limit as x goes to infinity. I chose to put e to the x on top and x squared on bottom. It does not matter which function goes on top and which one goes on bottom. You can come up with the same conclusion either way. Okay, both of those limits are infinity, so we apply L'Hopital's rule. I get e to the x on top, I get 2x on bottom. Both of those limits, again, are infinity. Apply L'Hopital's rule again. I get e to the x over 2, which approaches infinity. So I can conclude that e to the x grows faster than x squared. Look at this graphically. Here's the graph of y equals e to the x over x squared, and you can see at some point that e to the x really takes over and this whole thing takes off towards infinity. Okay, growing at the same rate is transitive, meaning if a grows at the same rate as b and b grows at the same rate as c, then a grows at the same rate as c. We can formalize this right here. We have the limit as x goes to infinity of function f over h, that equals a constant L sub 1. Those grow at the same rate. The limit as x goes to infinity of g over h equals L sub 2, another constant. They grow at the same rate. Then I can conclude, even though I didn't show it directly, that f and g also grow at the same rate.